Morning, everybody. Welcome back. Hope your weekend was okay. Your week is not going to be because you have an exam on Thursday, right? I have, as yet, not been called into jury duty. So I figured after today it's pretty safe because if I get called in tomorrow, I'll just cancel lab. And you guys would probably be very happy about that. And then if I do get called in on Thursday, I've got Mr. Evans ready to go to come in and administer the exam. So I think we're off the hook in terms of all of that, so you can expect an exam on Thursday. Let's see here. What else is going on? I have to tell you about. Pi Day show. The annual Pi Day show is happening this Friday. Pi Day is on Thursday, so you get to take your exam on Pi Day. But the show that we do here at the school, where you get to see professors pied in the face, is taking place on Friday. I believe that's 12 o'clock at the main fountain. And people have been asking me, no, I'm not in the list of professors to get pied for two reasons. I was on that list for like 12 years and I never got pied. My students always made sure that I was always in the middle of the pack. And they didn't want to see me pied for some reason. I don't know, some of you were like, yeah, I'd pay money to see that, Mr. Balogh. And then one year, one student's like, hey, can I pie you? I'm like, sure. So they pied me. The other reason is that I used to do the pie show, like to be the main person, but now I am the safety officer. And so it's kind of hard to keep people safe and keep them from blowing themselves up if you've got pie all over your face. So that's, I'll be running around behind the scenes on that day. Let's see. Exam, lab tomorrow. Lab tomorrow is kind of a big lab, kind of a long lab, just so you're aware. Be able to time things out. Somebody sent me an email requesting, hey, can we do like homework like we did last time? I think it's a fantastic idea, but I just haven't been able to figure out how to make that work this time around. I'll look into that for next unit, moving into the exam. But yeah, I do like that idea. All right, what are your questions for me? Things you have to know. Yes, sorry.
Can you go over torque?
Yeah, so it just, there's two things right there, right? Okay, and it's like double torque, right? So I put down there static equilibrium and then not equilibrium. Okay. Tomorrow's lab in a lot of ways is the not equilibrium part. But what do I mean? So what is static equilibrium? What's going on there that's like special? No acceleration whatsoever. And now we've got two types to worry about, don't we? We have the linear acceleration and we have the angular acceleration. So in static equilibrium, we set both of those things to zero, we apply torques and forces, and away we go. And I'll do an example of that. In the not equilibrium case, let's see, in class I did the, was it the potter's wheel? This is the case where we do have alpha, and we've got to worry about the moment of inertia, and there's a homework question that's tugging at my brain. So like, this is a static equilibrium problem, this is a static equilibrium problem, this is a static equilibrium problem. Okay, here, so this is almost exactly, well, the one I did in class got a little bit more detailed in that we used torque and angular acceleration, moment of inertia, to find a coefficient of friction. This is simpler, okay? And this is an example of a problem where you're doing torques where it's not in equilibrium, okay? That's number 8. This is just moment of inertia, that's conservation of energy, conservation of angular momentum. Here's a static equilibrium problem, static equilibrium problem, static equilibrium problem. So I leaned heavily into the static equilibrium problems on the homework, okay? But when it comes to this concept and idea of torque, I mean, you've really got kind of, I don't know if you want to think of them as like two big problems. So let's see here. I'm gonna answer your question, Soraya, I'm gonna get there in a second, right? But let's just go through these topics really quick. Center of mass, okay, you did a whole lab on that, right? So I put a question on the exam that involves you finding the center of mass of the system, okay? Personally, or just in relation to the other things on this list, I wouldn't call that a terribly long problem to do. As long as you set it up correctly and do the math correctly, away you go. But it's a fairly quick setup, all that kind of stuff. Rotational energy conceptual. Again, it kind of depends on you and how long it takes you to do a conceptual question. If you got to sit there for 10, 15 minutes agonizing over the answers, that's up to you. But this is like the example I did in class where I rolled the two objects down the ramp, right? Okay, where we've got things that have energy not just moving in a line, but also because they're rolling. And then torque, not equilibrium, could be a big deal, but I think the longest problem on this list, the problem that's probably going to take more than 10 minutes, is the static equilibrium problem. They're just really involved problems, aren't they? I think the example I did in class with that sign hanging off the end of the beam took us like 45 minutes just to do that problem together. So, and of course, I've engineered the problem in such a way that the math goes much quicker. That you don't have so many unknowns to be looking for, and I will be looking, your grade will depend on how well you kind of get this thing set up, right? And it's nice to get the right answer, but not necessarily get the right answer. But I see torque as being one that's going to be a time sink. I would save that one for last, really. Rotational kinematics, in my experience, the feedback I get from students all the time is that something that it's a little bit weird, but I kind of got it, Mr. Balogh. Same way I kind of got kinematics before, I kind of got that one. Conservation of momentum can cause a little bit of difficulty. That's conservation of linear momentum. I should have put linear in there, right? Because we've got both angular and linear. And then impulse. The thing about impulse is that those problems are usually pretty quick. This is the change in momentum, force, time relationship. So usually pretty quick to calculate, but there is a huge trap in that impulse calculation, and it has everything to do with the direction that objects are moving before and after the collision. Remember, you're calculating a change in momentum, and momentum's a vector. So, if I take a ball and I throw it at the wall, and it bounces off the wall, right? And it's going in at 5 meters per second and coming out at 2. What do you have to do with the 2? It's got to be -2. Because if we say +5 into the wall, and it bounces away, we need to make sure we have a negative sign on that velocity. And so over and over again in the impulse problems, I see students being loosey-goosey with directions. Right? Pick whatever direction you want to call positive, that's fine. But if something reverses direction, you got to make sure you get an opposite sign on it. So by and large, right, and you kind of can think, you can sit there and go, okay, you can put these like on your cheat sheet, right? And then if you want to spend just a few minutes like lining up and looking at all the questions and going, okay, that's a statics problem. And how do you know it's a statics problem? Like, what's going to be a giveaway that it's a statics problem? There's going to be no acceleration. There's going to be a situation where there's like a beam or a ladder or something, right? And it's going to be attached, or somebody's going to be on it or something, right? But it's not doing anything, right? It's just hanging there, okay? And you'll be like, okay, that looks like a statics problem, right? And so I can save that one for the end, right? But again, maybe statics problems are easier for you, right? And you just want to bang that one and get it out of the way. I want to help you pace yourself, right? And go through that exam in an order, do the problems in any order, and do the ones that are easier for you to do right off the bat. And if you're getting stuck on a problem, just move on. right? Move on to a different problem, come back to it later. Your brain will enjoy that. Okay, to Sarahi's question, right, and talking about torque and just sort of going over it, should we tackle a couple of the homework questions? For all 23 of you that still haven't started the homework? All right, so let's see here. This one usually throws people for a stupid reason, so we'll talk about this one. You know what? I really probably should have not gone through and shown you all the answers, but oh well. That's how it works. Oh, is it right? Expand question. There it is. That should just be done by default, and don't give me a button for it. Okay. So, statics problem because this person isn't accelerating. They're just sitting here planking, okay? And what they want us to find is the force on each hand and each foot, okay? So, to set this up, first thing we got, okay, so two things that we've got to do in this problem. We have to make sure that we add up all the forces and that they end up being zero, okay? And that can happen in two directions, X and Y. And then we need to make sure that all of the torques add up to zero. I'm going to go pretty quickly on the force one because we've just done it a lot, and you can go back and see chapters 4 and 5 for that. So in terms of forces acting on the athlete here, I've got I'm going to call it N sub F for feet, okay? I've got the weight of the athlete. Oh, well, they just say W. They don't give me the mass, so we'll just say W. And then we'll do normal force of the hands, okay? So I see 2 points of contact, and I see gravity pulling down on the athlete. I don't see any. Their trainer isn't shoving, putting heavy masses on them or anything like that. So that's what I've got. And if I'm going to be talking about forces, I do need to give a coordinate system of some kind. Since there's no horizontal forces here, I'm liking life. This is going to be good. So let's see here. In the x direction, 0 equals, instead of ma, it's just going to be 0. And I got no forces in the x direction. I like it. Vertically, I'm going to say nf plus nh minus w. Okay, so I'm going fast here, and I did something pretty dangerous. I did directions and forces at the same time, right? But check me. How did I do on my directions? Am I good? Feeling pretty confident about that. Okay. All right. So I'm looking at that, and I'm going, okay. I've got 2 unknown things. I don't know what either of these normal forces are, and I really only have one equation to help me out. So I've got to figure out another equation, method, something that's going to help me eliminate some things. And so what I'm going to do is I'm going to do torques. Okay? And a torque is a single equation. Okay, so this is the new part, right? In chapter 9. What do I need to, I got to do 2 things before I can even really think about torques. What are the 2 things I have to set up or choose? An axis? Rotation. And a direction, like what am I going to call positive, right? So, excellent. So, axis. Put an axis at the greatest number of unknowns. The feet or the hands, right? It's like, whatever. Okay, the feet. Just could have been feet or hands, doesn't matter. I might end up doing both here. Let's see. So this is my axis. I'll label it to make sure I can remember where it is. And then pick a direction for positive rotation. Your choices are clockwise or counterclockwise. Clockwise? Counterclockwise? You guys like sticking with your normal units, don't you? That's fine. It's what you grew up and what you're used to. Okay, so With those two choices in place, I can now go through and start talking about the torques acting on the athlete. Okay, so hold my pencil, right? Like the athlete there, and the normal force from the feet, how much torque does it apply? 0. It's right at the axis, so I don't have to worry about it. Okay, weight, it's pushing, it's pulling down or pushing down. I can either pull it down or I can push it down. As long as I do it down, which way is the pencil rotating if I do it like that? That's clockwise, so that's going to be a negative torque, isn't it? And then, what about the hands? It's up. Okay, so do I have opposition there? Can I get to 0? Yeah. So like what I'm checking here is to make sure that I haven't missed something, right? And then I'm just going to, just really quick, not going to draw it. I'm going to throw an axis at the hands. And again, normal force from the feet is causing clockwise. The weight is causing counterclockwise. Again, I have opposition there. I'm feeling pretty confident that I've managed to remember, or at least locate all of my forces. If you ever end up with an axis where you can't balance the torques, something's gone wrong. Then you got to go back and figure out what that is. Okay, so with that axis on the end, I really only have the weight and the hands to worry about. So it's going to be a torque due to the weight and a torque due to the hands. I just sort of separate those out, leave some blank spaces, go back, do the direction separately, but I've kind of already done the direction, right? The weight is going to give me a negative torque. We said that counterclockwise was positive. The weight is causing a clockwise torque, and so I'll put a negative sign on it. The hands causing a counterclockwise torque, as I push up on my pencil, will make that positive. Okay, so established the fact that I can be static, in that I've got opposition, found out what those torques are conceptually, and gotten their directions done and out of the way. Okay. Now I've actually got to think about what the torques are. Like mathematically, how do I express a torque? And I taught you that we do an R perpendicular to an F, right? So we need a force and we need a distance, a perpendicular lever arm distance to that force. So for the weight, okay, I know the force is W. What's the distance to W? Yeah, it's the 0.84 that they showed me in the diagram, right? I mean, I know my perpendicular distance to that weight, so it's going to be 0.84 meters times W. Plus, and then what's the distance to the hands from my axis? What's 8 plus 4? 12. So 0.84 plus 0.41, 1.25, I think. So there's my distance, and the force at that distance, it's the normal force from the hands, right? Okay, so there's my setup, right? And in that green equation, oh, where did I get the 1.25 from? You add together those distances. I need the total distance from my axis to where that force is being applied. Okay, so in that green equation, how many unknowns do I have? 1. We know the weight, don't we? They told me the weight of the athlete's 512 newtons, right? So the only thing I don't know in that equation is n sub h. So that means I can solve for n sub h. Once I solve that for, what am I doing right now? I'm planning. I'm doing it, I'm planning, right? I'm going to solve the green equation for n sub h. And once I've got n sub h, the normal force on the hands, I can go in and with the red equation, the y red equation there, I know the weight, I now know the normal force on the hands, I can find the normal force on the feet, right? And then I'm going to go dump those numbers into those boxes and it's going to be red. And why is it going to be red?
For each hand.
They italicized the word each. Okay? So what we did is we found so let's say that the normal force on the hands ends up being, I don't know, 200 newtons. Okay? What we found is the normal force of both hands acting together. assuming equal distribution, what would be the force on this hand? If the total's 200, 100 on this hand, 100 on this hand. It's that word each in this problem. I'll get emails from you. Mr. Ferreira, why the class hates me? I did it all right and it's the wrong answer. I was like, well, did you divide by 2? It's that word each, right? 2 feet, 2 hands. Spreading the load, okay? So, I don't know. I mean, I think I can guess why they wrote it like this. They could have just said, what is the normal force on the hands? What is the normal force on the feet? And be done with it, right? But they were trying to be extra tricky. I think this is the way that physics textbook authors assert dominance over other people. Stupid. Okay, so there's an example of torque doing static equilibrium. Okay? Now, in terms of difficulty here, I'd say that this is a really decent exam problem. This is right in the middle. It's not super duper hard because we didn't have to find any components or anything, right? It's not too easy on the other side. The algebra was fairly straightforward, right? And would be a good type of problem for seeing whether or not you can figure out torque.
So we'll basically be using torque as another tool for solving the second law.
Yeah. I mean, torque is the second law. It's just the rotational version of the second law.
Can we carry over the signs we had for our forces for torque?
No, they are separate. Forces obey X and Y directions, right?
Just in this instance, it was the same.
By coincidence. Yeah. But yeah, torques are all about clockwise, counterclockwise, and forces are all about that X and Y direction.
And those signs are just based off of what you call.
Exactly right. It's what we choose for the axis directions. And so in that sense, it's quite arbitrary, right? It actually doesn't matter what we pick for positive X, positive Y, and positive torque. What matters is once we pick those things, whatever direction they are, we obey those directions. That's what I mean by stay consistent. You want to pick something and then obey that, right? And you'll be fine as long as you do that. The exception comes from when we don't have the static case. And then we've got to be really careful about how we, okay, so we'll do this one, why not? We've got to be really careful about how we define positive because we want to do that in the same direction as the acceleration. That's really, really important for keeping your signs straight. So Potter's wheel, again, just sort of visualizing here, right? We got a wheel, okay, and it's experiencing a torque. And we want to find the moment of inertia. This is a pretty quick one. All right, so they don't tell us. Well, okay, so this is the vase, right? The vase on the potter's wheel. So I'll just draw something here. So here's our vase on the potter's wheel. Okay, which way? This is seen from above. Which way is this thing spinning? Clockwise? Sure, why not? It doesn't matter, okay? They didn't tell us which way it's spinning, and so that means we're sort of free to pick kind of our situation. So if we say the whole thing, right, is spinning this direction, I'm using omega here as my indicator for angular speed, right? They're telling me that this vase experiences an angular acceleration due to this amount of torque. Again, they haven't really told me whether it's speeding up or slowing down. I'm going to guess that it's speeding up, maybe they're turning the potter's wheel on. So if it's spinning that way, I'm gonna say, okay, well, my alpha's this way, like it's speeding up. They don't tell me initial and final speeds, but they give me my alpha, right? 5.7 radians per second squared. Okay. If that were the case, then what direction is the torque going to be if this thing is speeding up? There's only one torque, the one they gave us. So what direction is that torque acting in order for this thing to have an alpha that is clockwise?
So clockwise?
If the torque were counterclockwise, that would be acting against the direction of motion. So we have angular speed, we have alpha going in the same direction, which means it's speeding up. Here's my base, right? How do I apply something that would make this thing have an alpha that goes clockwise? Down or to the right. I would also have a clockwise torque. You can also think about it if you want an equation to do it, okay? This is Newton's second law in rotational terms. Just like Newton's second law in linear terms, where the net force and the acceleration share the same direction. If something is being pushed from behind, it's going to speed up, right? The acceleration is going to be forward, the force is going to be forward. Torques and angular accelerations follow each other. The net torque. Now, there could be 3 or 4 or 10 torques acting on this thing, but if this thing is accelerating in the clockwise direction, that means that the torque, the net torque, has to be in the clockwise direction. Otherwise, Newton's wrong, and that's okay. Newton can be wrong, but annoyingly, he's not. So anyway. I have alpha, and I have the torque. What do they want us to find? Moment of inertia. Well, I'm staring straight at this equation going, wow, okay. My moment of inertia is going to be my torque divided by my angular acceleration. They gave me the torque. 16.4 Newton meters. They gave me an acceleration, 5.7 radians per second squared. At this point, I'm starting to lose a little bit of my sanity because there's no way it can be this straightforward. This is physics after all, right? Can't be this easy. I mean, they even gave me standard units, didn't they? Like they didn't try some weird thing with revolutions per minute and foot-pounds or Newton centimeters or some weird unit of torque or any of that kind of stuff, right? So my fingers are starting to shake just a little bit on my calculator. But nonetheless, this is exactly how short this problem is. 16.4 divided by 5.7, and it should be equal to 2.877. Yeah, I can believe that, because 6 into 16 is going to, yeah. So that's that. Take a look at this problem. Take a look at the potter's wheel problem that I did. I didn't do that on purpose. In class, okay? And you'll cover the gamut of what I mean by torque, no equilibrium. So Sarahi, did I answer your question? It only took a half hour. Okay.
Did you go over question 7?
7 from this chapter 9?
Yes.
Let's see. 7. Yeah, okay. So here's one that's got this is a little bit more involved. I can just kind of, looking at it, I can sort of see it, right? That, for some reason, that drawing is impossibly small. Don't know why it's doing that. So let me do this. Did I do it right? Yes, I did. I could flip back and forth. Okay, so I'm going to try and recreate this beam and its hinge and all that kind of stuff. So here's the beam up against the wall, that hinge right there, and then there's this bar, the brace, and the angle theta that they gave me is right there. Okay. What have they told me? Drawing shows beam attached to a wall, frictionless hinge, brace, beam. Okay, so the beam has a weight. Let's take care of the weight first. Where is that weight going to be applied? Like where do we draw the weight acting from? Very center. If you're not told anything else, then you just assume it's the center of mass, uniform, meaning it's the same throughout. So that means that, oh, and why am I going to draw, I should have started here. Why is the beam, the horizontal beam, my central member? The thing I want to draw forces on. It's touching everything, right? Like the brace is touching the wall and the beam, but the beam is touching the brace and the wall and gravity and all that kind of stuff, right? So, again, finding that thing that's at the middle, really important. Okay, so what did they tell me? They told me that the beam has a weight of a certain number. Great. Okay, what else have they told me in this problem? 3 additional forces. Oh, they're giving me hints. 3 additional forces keep the beam in equilibrium. They can tell me what they are. The brace applies a force to the right end of the beam and is directed upward at that angle. So there is a force, P, that acts up like that. That's what I got from the brace to the right end of the beam. You had to direct it upward at an angle with respect to the horizontal. So this is what they're trying to communicate to me right there. Okay? And that angle is theta. Alternate interior angles are equal. Geometry is a killer. Okay. The hinge applies a force to the left end of the beam. Oh, that has a horizontal and vertical component. Oh, so nice of them. Horizontal and vertical components. Oh, okay. Okay. So how do I know what directions those act? Did they give me anything about that? No, they didn't. They didn't tell me anything, okay, about that. But I can see I've already gone wrong. So let's figure out where Mr. Balogh made his mistake. Anybody see it?
Horizontal.
The horizontal force is wrong. The one I drew at the wall is wrong. How do I know? We have to make sure, in the end, that all of the forces add up to 0 in both the x and y directions. P has components, doesn't it? You see what's wrong here? That h and that px, we wanted to call that the px, and this is the py component, right? Px and h are pointing in the same direction. They're the only 2 horizontal forces in the problem. And if they're both pointing in the same direction to the right, and if we call to the right positive, we end up with adding 2 things together that are positive. Can you take 2 positive things and get 0? No. So I made a mistake. And the mistake has to be this one. It's not P because they told me that that P force acts up and to the right. So it must be that that horizontal force acts to the left. You're like, Mr. Balogh, there's no possible way I could have known that. Well, now you know, right? When you're looking at your horizontal forces, make sure that you can conceptually get them to go to 0. There's got to be opposition along the horizontal direction. Vertical, do I have opposition in the vertical? Do I have things pointing up and things pointing down? Sure do. Okay, and then we need to do torques as well, but let's do these horizontal forces first. Let's see here. In the x direction, I have h and I have px. H is negative, px is positive. And then in the vertical, looks like I've got v, which is pointing up. W pointing down, and PY pointing up. I think I got all of my forces there. Yep, PY up, PV. Yep, I got all my forces. And now I can come in and go, okay, what's going on with the torques? Got to add them up to 0. And Problem probably wants to know everything, doesn't it? They usually do. V, P, and H, yeah, okay. So, axis choice. Where should we put it? Hinge or P? Hinge? I kind of like the hinge. I mean, the rule of thumb here is you always pick the point of greatest number of unknowns. And failing that, you pick the point where you think the thing would rotate anyway if something were to fail, right? That brace somehow failed, okay? So I'm going to go ahead and stick my axis right here. And I won't even ask anymore. We'll just go counterclockwise for positive. All right, so that's my axis. I don't have to worry about H and V. That's nice. Let's check and make sure I can get 0 torque. I have opposition in my torque. So the weight causes a clockwise rotation and PY causes a counterclockwise rotation. We're in good shape. Why am I not checking PX? It doesn't cause torque, right? Okay, it's not perpendicular, okay? All right, and then just check another, I'll do the other end just to make sure here. I've got V giving me clockwise, and I've got weight giving me counterclockwise. So again, I have opposition. And since they told me the number of forces I have to have in the problem, I don't know, I'm pretty confident that's going to be what it is. All right, so let's see here. I'm going to think about my torques. I'm going to have a torque from the weight, and I'm going to have a torque from PY. Now I'm going to go through and I'm going to set my directions. We already said that the torque due to the weight's causing clockwise, so we'll call that one negative. And PY, yeah, positive. And now I go through and I'm going to actually kind of mathematically write in what those torques actually are. So do they tell me anything about the length of this beam? No. I've either misunderstood or it's not important, right? I usually go for I misunderstood and I'm the problem. But I'm trying to grow up and get over that. So if that's the case, I'll just leave it symbolically and hope that my symbol goes away somehow. So what is the distance from the axis to where the weight is acting? Looks like it's half the length of the beam, isn't it? So I'll just say L over 2. And then what's the force? Weight of the beam. Okay, what's the distance to where PY is acting? Well, that's the total length of the beam. And the force is PY. It's an algorithm. I've done this algorithm now for you several times on all of these problems, right? And by algorithm, I mean it's very much like a computer algorithm. It's a step by step. I do this, and then I do that, and I check my directions, right? And then sometimes there's a for loop or a return where I have to go back and run the algorithm again, especially if I made a change. But it's a systematic approach, right? That's what I've been trying to teach you all semester, these systems and these approaches. Hopefully you're getting to that point where you're starting to see a little bit of that system and you're still not just throwing equations at the page just to see what happens. Although I know that's what you're doing too because I grade your exams. So it's not that throwing equations at the page is bad, it's just not great. Okay, so let's see here. Am I saved? Can I use the equation in blue? What do I know? They gave me the weight, didn't they? Don't have the length of the thing, do I? But can I be a little bit clever? What happens to that length? Cancels out, doesn't it? I mean, mathematically, I divide every term in the equation by L. What's 0 divided by L? 0, right? And then all the other L's will cancel out. So it ends up not mattering, which is a good thing because they didn't give it to me anyway. What does this say? This says that Py is equal to 1/2 the weight. the weight they gave me, 342, so whatever half of 342 is gonna be Py. But what's Py? Like, what's the relationship between Py and P if it's not touching the angle? Sine. So Py is equal to P sine theta. And so now I can find out what that P is. It's Py divided by sine theta. And now I know what P is. And now that I know what P is and Py, how do I find Px? Cosine is touching the angle. P cosine theta, right? So now I can put Px into there and find H. I can put Py into there and find V. And I've got V and I've got H and I've got P. Put them in the boxes, see if it's right. On the exam, don't have a box to turn green for me, so hope and pray. It's hard to check these things, right? The checks really have to be kind of in the beginning where you're checking to make sure your forces can add up to 0, your torques can add up to 0. And you know me well enough by now that my grading method is screw up in the math, okay, right? I'm not a math teacher. Screw up in the physics, I'll come after you. Juan?
So we're good to like put I guess our values of Py into our just linear thing?
Yeah.
Doesn't matter.
Yeah, you found Py. It didn't matter if you got it from the torque equation or not. I mean, that's where you're gonna get it from. It's the torque equation.
Even if like we're given like a distance, where like now it's the force and the distance is still equal to that.
Yeah, I mean, if you know that distance, you can still solve for that torque, right? So torques, right, are distances, in this case L over L times Py. Well, this is a distance R times a force, right? And if you know the torque, you can solve for that force. That's fine. Yeah. That force is that force. The fact that it's acting at a distance makes it a torque.
Oh, so I got you.
But it's still a force.
So our certain distance is separate from that, so we wouldn't include that in the linear.
Yeah, I mean, here, where was it? This thing right here, Py. Notice all the distances went out. If I knew the length of the beam and the weight wasn't in the center, I would just put the numbers in, and then there would just be numbers moving, along for the right.
So because you find Py, do you still have to solve for the P sine theta?
Yeah, because they asked me in the problem for P.
Oh, okay.
Do you see right here, they're asking for P? They don't ask me for Py, they don't ask me for Px. They ask me for P. Another way to do it is that you could get Px. Well, to get Px, you need P anyway, right? But you could do Px squared plus Py squared square rooted. It's longer. It all works. And there is no one way to skin a cat in physics. There's lots of different ways to do these problems. And you're probably confused because there's the way I do it and teach it, and then there's the way sort of the book does, which are close. Those are pretty close. But if you're watching any other sources on YouTube, they might have a different set of symbols, but the underlying approach is still the same. They have different names for the steps, and they might do them in a different order, but yeah, I know it's confusing out there. Sometimes too much information is bad. Like TikTok. I can't remember who asked this question, but did I answer it? Okay. Other questions? Yeah.
Can you go to number 12?
12. 9, 10, 11, 12. Oh, don't jump. All right. was going on? Okay, what distance can this person walk, right, before it begins to tip, right? So we've got some conditions here, right? Now, this is a static equilibrium problem, to be clear, right? Because they're asking us how far can they walk and still maintain this thing being flat and horizontal, but in the next instant, things are going to start tipping. We're not going to worry about the tipping part. We just want to know what's going to happen, right? So, let's see. What's the central member? What's the thing that's connecting every single object in this problem? It's the board, right? It's not the person. It's not the two supports. The board connects the person, the two supports, the planet Earth. It's all acting on the board. So we're going to draw forces acting on the board. Give me a force acting on the board. The person. Okay. So what direction is the force of the person on the board? It's down. The board pushes up on the person, right? But by Newton's third law, the person pushes down. So, not that pen. And let's see, the person, they just gave me the weight of the person, so I'm going to call that P. All right. And then, what's another thing that's pushing or pulling on the board?
Spikes.
The two spikes. So let's handle the one close to the person first. What direction is the force of that spike on the board? It's up. Holding the board, pushing up on the board. We'll call that N1. I called it N1 because there's going to be an N2. All right. Anything else acting on this board? Yeah, the Earth, right? And they say uniform plank, which is code language for where we draw the weight. Where do we draw the weight? Right in the center. And I reserved W for that one. Okay. So I think I've got all the objects pushing or pulling on this board. We'll find out later. Are we balanced in terms of forces? Do I have uppy forces and downy forces? Yes. Do I have lefty forces and righty forces? Technically yes, but no, right? Like there's nothing going on, so I don't have to worry about that. And then what about torque? So I just pick a spot, right? I'll pick the left end. And so W, okay, pulls it, what is that direction? Clockwise. P pulls it clockwise, but N1 does counterclockwise, right? So I've got opposition there, we're good. If I check let's do the other end of the board, doesn't matter, okay? I've got P is clockwise, counterclockwise. I've got N1 is clockwise, I've got W is counterclockwise, and I got it, okay, so it looks like I got opposition there as well, right? Those are my quick checks to just make sure that I can satisfy the conditions. It doesn't guarantee I've got all the forces, but by golly, if I've got torque that's not balanced, I've made a mistake somewhere. If I've got forces that are in opposition, I've made a mistake somewhere, like guaranteed. So I'm feeling fairly confident here that I've got opposition and maybe I haven't missed anything. Okay. There's something that's going to happen here, though, that I need to take into account. So as that person walks out on the plank, what's going to happen to the other end? It's going to lift off of this support on the left-hand side, isn't it? So what will the normal force be when that person's at the maximum distance? It's going to go to 0. So they're telling me that they want me to solve for the distance when this normal force goes to 0. So I'm going to, and because they've given me that condition, right? To what distance can they go before it begins to tip? If they said the guy was half a meter on that side, find the normal force at that end, I couldn't cross that out. So this is a specific condition for this problem. Important safety note, you should always nail down your planks if you don't want them to tip. Okay. So with that, I just want to make sure I've got opposition still, and it looks like I do. I got up forces, down forces, and my torques are still okay, even though I got rid of that. All right. I mean, this isn't going to really help me. You'll see why in a second. That's equal to 0, and the y direction just says that the normal force acting up is countered by the two forces acting down. Is there any distance in that statement? No. Some of the forces isn't going to help me find distances. I'm going to have to apply some of the torques. Okay, so torque. I need an axis and I need positive direction. What's the rule of thumb tell us about where we should put an axis? Where the most unknowns are. There's only one point where I see the most unknowns. Where is that point? Do we know W? Yeah, they gave us the weight of the plane, didn't they? Do we know the weight of the person? Yeah, so I don't want to put the axis there. Is there an unknown at the left end of the plane? No, that's 0 over there. The only unknown is N1, isn't it? So I'm going to put it there. Why not? All right, that's my axis. Axis. What's that? You want to do clockwise this time? Think different. It's good. Doesn't matter. Okay, so we'll go clockwise on the torques this time, and what have we got? From this axis, I will have a torque from P, and I will have a torque from W. Torque from P. So I'm going to take my plank. I'm going to hold the axis right there, right? Because it's kind of off-center just a little bit. And then P is acting down. So I either pull down or I push down. And which way is my plank rotating? Clockwise. And what direction are we calling positive? Clockwise. So that's going to be a positive torque. Okay? Axis in the where the fulcrum is. Now I do W. W is either pushing down or pulling down. Which way is my thing rotating? Counterclockwise. And what direction is that? Negative. So for those of you that are all bent out of shape, because we picked the other direction, I'll just do it this way real quick. Torque from P, torque from the weight, okay? If we do what you're used to, okay, then P acting down, causing clockwise would be negative, and then the weight would be positive. Those two equations are identical to each other. I can multiply either one by -1 through all terms and get exactly the same equation out. That's why I say it doesn't matter what direction you pick for positive. What matters is that you stay consistent with your choice. You'll be safe either way. Okay, so do we know what these torques are? We know the plank has a length of 5 meters. Oh, they're going to make me think to get the distance here, aren't they? So let's see here. The distance from there to there is 2.5 meters. How did I get that? That's half the length of the plank, right? So the distance from here to here is this distance is going to be 2.5 minus, and I've now written over it, but I think it says 1.1. Right? So whatever, that's 1.4, isn't it? Yeah, okay. So I know my distance is 1.4. Okay, so I can go ahead and write out this torque equation now. Torque due to P. What's the distance to the person's force? You've already forgot what we're solving for. We're solving for that distance, aren't we?
Yes.
So it's gonna be x. Unknown. Pick favorite symbol here, right? So it's gonna be x times that force. That's the torque, minus, now what's the distance to the weight? 1.4, and what's the force? W. I know P, I know W, I know 1.4. The only thing I don't know in that equation is X. It's all for X. This problem can be solved using center of mass. The center of mass is just torque hiding. You can put the 0 point for the system center of mass at the fulcrum, and then you can just use your center of mass equation from there. Either way. The question. How you do with the time change? It's not good, is it? It isn't just not good. I blame Congress. I do. I blame Congress for a lot of things, but this is one that I factually, legally can prove is their fault. Because they're in charge of the laws, and the law is dumb. So, that's not opinion, it is dumb. Do you know that there's a 10% increase in traffic fatalities on the Monday following the change to daylight savings time? That is in the record. 10% more people die in automobile accidents on that Monday.
Also heart attacks.
Yep, heart attacks go up, blood pressure measurements go up on that day.
What is it? Give my son.
Okay. Does the amount of sun in a day change just because we move the clock an hour? No. No, that is not what happens. Is there more sun available after the magical 5 o'clock get home from work time? Yes. Which is usually what people mean when they say something like that, right? No. There is only one reason to change the clocks. Money. What happens when people have more daylight after work? They shop. They spend more money on gasoline, on entertainment, on being out.
So why don't we lose it now in November?
Because people whine about how it's so dark at night. Again, money. What?
Don't you have like, let's say it's like 4 in the afternoon and now it's dark? Aren't you losing, I guess, theoretically?
Does anybody know why daylight savings time started? Okay, does anybody know who to blame? Answer Ben Franklin, okay? Second, because he's the first one that proposed the dumb idea. Number 2, daylight savings time as we know it today got started in World War II. You better ask me a physics question, otherwise this is going to take a while. Started in World War II because at the time in the United States, overtime law said that you got paid overtime if you were working when the sun was below the horizon. Okay? So if the sun sets, right, then you are owed overtime. In summer, we would switch not to single daylight savings time, but to double daylight savings time. We would shift the clock 2 hours. We'd shift it in the spring, and then we'd shift it again in July, so that 2 8-hour work shifts could fit in the time span when the sun was above the horizon, so that companies didn't have to pay workers overtime because companies were running 24-hour shifts to support the war effort. So the shift in these times has nothing to do with biology. It has nothing to do with farmers. Everybody blames the farmers. The farmers are against daylight savings time. They want overtime pay. It's all about saving money. Or, as the modern term form is it, getting people to spend more money and stimulate the economy. The other reason that is often said is it saves energy. What do you know about energy? It is conserved. There's a set amount of energy. What they're trying to say is that people will shift their energy consumption from electricity at home to electricity elsewhere. Okay? Again, it's this shift in behavioral pattern that takes place. Okay? It is approximately 50 years too late for us to change this. This should have changed 50 years ago. With artificial illumination, the fact that overtime is no longer classified by when the sun is up, and the fact that everybody hates it. Like everybody, you want to unite America, okay? There's like 70% of Americans believe the clock should stop changing. When was the last time 70% of Americans agreed on anything? Well, besides the Oscars, right? Like it's, if you want a bipartisan win, just do that, right? There's only 30% that's going to be mad at you. Everybody else is going to be happy. So we are beyond the point where this should stop changing. Scientists, my brothers and sisters in the physiology, anatomy, physiology, human behavior, sleep areas, biologists tell me that it's actually better for our human person to have light earlier in the morning. Like it's better for us waking up, it's better for productivity, it's better for IQs, it's better like all those kind of things. Which is why you will see scientists pushing for a removal of daylight savings time. Like, don't go to daylight savings time, just stay on standard time all the time. Which does mean for us here in California, darker evenings and lighter mornings. I feel for people that live in, say, North Dakota, where it's much more extreme. Like they'll get like, if on standard time, it's like the sun sets at 3:30 in the evening or something like that, right? Because they're just more north. But the other problem is that they're in North Dakota. I mean, seriously, just go somewhere else, okay? So yeah, I actually don't care where we go. Standard, at this point, just stop changing the clock. Just stop changing the clock, right? Daylight, standard, whatever. Rant over. What am I doing? 5. Did I sound too much like an old man? I provided facts, right? My opinions are based on like facts and evidence. I don't just try to throw my opinions around and say, well, it's my opinion, therefore it's right. All right. Let's see. Always go for the data. Which one am I doing?
The tree one. I think it's number 5.
Dumb kids. All right. This is my daughter, actually. She's 3.5 years old. Managed to climb about 25 foot up a tree in our backyard. My wife, I had to lock her in the house, right? My wife was beside herself, right, with terror that our daughter was going to fall out of the tree. My daughter was up there, hey, Daddy, look what I did. I was like, that's great. I'm not coming up after you. And she started bawling. Oh, like, you climbed up, you climbed down, you got to climb down. And I walked back in the house. Restrained my wife, right? Watched as my daughter climbed back down. Don't call CPS. I'm a good dad. It's just, kids got to learn. All right. Besides, she would have bounced on like a dozen branches by the time she got to the ground. Let's see. And kids are made of plastic anyway. Let's see. What is the magnitude of the torque exerted on the branch by the children? And they're telling us the axis has to be where the branch joins the trunk. and it's perpendicular even though they did not draw it perpendicular. Thanks, guys. Okay. So basically, what have I got going here? I have tree. That's all I got. Sorry. And then I've got branch, and they said it had to be perpendicular, right? Okay. And they want the axis right here. And no, but they gave me an angle. What are they talking about?
You're gonna find components.
Assume that the axis is located with the branch and the tree, and it's perpendicular to the plane. Oh, they're being mean. Okay. The axis runs perpendicular to the page, is basically in or out. This is a stupid way to say that. Okay. And then we do have an angle. Right here, theta. We've got a kid that's at some distance. Let's say M1G. And then the other kid is at some different distance. M2G. 2. There we go. Find the total net torque. Okay. By the children. Okay. Because my initial thought here is that the torque is 0. Right? If the kids are hanging from the branch and the branch isn't breaking off, this is a statics problem and the net torque is 0, and so the answer is 0. I'm done. But I think what they want is, it says by the children, right? So basically we just want to find the 2 torques that these children are exerting on this branch. They gave us the distances along the branch, didn't they? They gave me a D1 there, and they gave me like a D2 right there. So if I'm going to find the total torque, I've got to find the torque from kid 1 and the torque from kid 2. No matter which way I pick as positive or negative, what can you tell me about the directions of the torques from the kids? They're the same, right? So I might as well just call them both positive or both negative, or it doesn't matter. Okay? They want the total torque. As a matter of fact, in the problem, did it ask for like a direction or anything? Nope, they don't say anything about that. Oh, they say magnitude of the net torque. So they didn't even care about sign, right? So I'll just call them both positive. They're not in opposition to each other. If they were in opposition to each other, one would have to be negative, the other would have to be positive. Okay, so we're going to find this. And to do that, I need a distance, right? I need a distance to kid 1 and the force of kid 1. What's the force that kid 1 applies to the branch? It's their weight, right? That M1G. So it's the distance times M1G plus the distance to the second one times M2G. You'll notice here I am not using D1 and D2. Why am I not using D? Why have I put R in there? I need the perpendicular distance to those forces, or the perpendicular component of force to those distances. Either way it works, I'm going to do perpendicular distance because that's what your book does more consistently. What do I mean by that? Remember, a torque has to be a distance and a force that are perpendicular to each other. And if I go, I'm just going to go over here. Here's M1G acting down like that, and here is D1. Are those two things perpendicular to each other? No. I need this distance right here. I need the perpendicular distance to the force. I know that the angle is 27 degrees. 27 degrees right there. And I know the length of the hypotenuse. Sine or cosine? Cosine, it's touching, isn't it? The unknown perpendicular distance right here is D1 cosine 27 degrees. So my R1 is D1 cosine 27, and then I've got an M1G on it. Okay, what about the distance to force number 2? Again, I can draw another diagram, find my perpendicular distance, my angle still 27 degrees, this is D2, what's this side gonna be? D2 cosine 27. Times M2G. And now I should know all of those things. I know the distances D1 and D2, I know cosines of 27s, at least my calculator does. I was given the masses, and I know what planet I'm on. So, calculate it out, that should be it. You can instead do do I really want to show you that? You can do perpendicular components to those distances. You might want to shut your ears for just a second. Here's the tree branch. Here's M1G. Here's my distance D1. I can also find the perpendicular component to that distance. And we've done this before. We know how to do like the normal force and gravity's components and all that kind of stuff. This is M1G cosine theta, isn't it? So now that torque from number 1 would be D1 the distance times M1G cosine theta. Notice, no matter which way I think about it, perpendicular distance or perpendicular component of force, I still end up with the cosine. Torque is torque. And, just to prove my point, in the book it says that torque is R times F times sine theta. Here it was cosine theta. That's because that sine theta in that torque equation doesn't mean what you think it means, which is why I don't teach that. I teach find perpendicular distance or perpendicular components of forces, and then you'll never have to worry about whether it's sine or cosine. All right, I will see you tomorrow unless I'm in jury duty, in which case you'll get an announcement around 5:30, if I am called in. If I'm not called in, no announcements. Lab number 9 tomorrow.